welcome to our second video on momentum. Okay, so we talked about the definition, and then this is second law, and this also second law, right? So this is the differential form, this is the integral form, and the right side of this thing is called impulse vector, just like right side of this is just force, and the right side is impulse force vector. So it's vector, so this is also a vector. And we talked about how to take care of in terms of when you do calculation, you want to say I've got a coordinate system x, y, z, and any vector can be, you drop it, and so this is the vector in the plane, and so this is the ax part. You drop in the y, you get 90 degrees here, ay part, and you drop so that 90 degrees over here, and then you get az part. The a vector, sometimes we say it's got the three parts, ax, ay, az, and often just one of them is important. These guys are 0, two of them important, and this guy is 0, this guy is 0. And so most cases we'll just be dealing with either 1 or 2. I'm really going to do 3, okay? So all these vectors, these guys, this guy, all the vectors, so they all can be treated like that. Okay. So we want to talk about momentum conservation in this video. So momentum conservation, there are deep principles why momentum is conserved. And when you take a course like classical mechanics, which will be probably second course, you might see that there. And if you take one more classical mechanics, again, then in this part you're going to see some really deep things about why momentum is conserved. But suffice to say, we already here you can say what momentum conservation looks like. So very conservation of anything, let's call it a blah. What does blah conserved means? So blah, let's think of at instant has this value. So conservation means that blah at some instant, initial instant, is same as blah at a final instant. And even more, so this is one interpretation, that the two instants, maybe something happened between, you got same as later. Another more valid way to look at it is, I thought blah depends on time, but blah does not depend on time. So it's for every pair of initial final is 0, is same. So blah is independent of time. So it never changes. That's a conservation, okay? So when we say momentum is conserved, in a situation So this I'm calling in a situation, we mean a P final equals to P initial. Sometimes we say total of everything. So this is in a situation. But momentum is conserved as long as you look at everything, okay? So it's always conserved. So in not just in a situation, but in all situations will be conserved, okay? As long as you broaden out your system. So this is in all situations. You want to think of all situations, then so you have an isolated system. I mean, there's no external forces. Forces on system, say system, let's call it system S. It may have one particle here, one particle here, one particle here, maybe a box over here. So this together, everything is together. Maybe you have Earth here, and maybe you have a star here, whatever. Everything is included. Forces on S, on isolated system S. So such a system, there is no way to change its momentum. There may be forces, internal forces, do not change the momentum of the whole thing. So basically, claim is internal forces alone cannot change the total momentum. Okay, but this very abstract, and we'll see where it comes from, and this application of this is in collision. So collision is an example of this principle, and we're going to talk about that in just a moment. Okay, let's get back to here. It's in a situation. So how do I look at this? So this one is very easy to see. Let's look at this law. So so you have a PF minus PI is impulse. Now, in this situation, this gives you 0 if that means if the impulse is 0 between this initial to final, if this is 0, then of course it's in this situation momentum did not change. But this is not what we mean by conservation momentum, but this just happens to momentum final the same as initial because impulse was 0. It's not like for instance, here's a situation this you will definitely find is say look at the x part, say x only. So x only will be pfx minus pfy equals to jx. So if you look at this and you have 0 sometime t and this f0, and here's a minus f0. You flip the direction, you come down here and go to 2t. So this is tf and this is ti. So this one gives you, this area will cancel this area, and j I to f is going to be 0. Okay, so this will mean whatever the momentum when we were here is the same when you were at this instant. That means a px at 0 time, px at t equals to 2t times in this situation. So the momentum did not change, but we don't mean momentum conservation by that. Okay, so now let's look at the momentum conservation in all systems. What is that law? And how do you look at it? Okay, so imagine you have system 1, say this is M1 or something, and you have M2, and to keep it simple, okay, let's see over here. Maybe so this is how it's connected outside, and then these guys gravity between them, so there's a force between them. So this one is system 1. If you look at the force, there's a force like that. If let's call it, I'm going to call this let's call it G1. I got even better example, okay, but and there's a force on this, I'm going to call it G2, and then there's a force between here on this in the line of connecting between them, force on 1 by 2, and then third law says there should be force on 2 by 1 if 1 2 is on 1 by 2, that's my notation. If 2 1 is on 2 by 1, and of course F 1 2 is same as F2 1 magnitude wise, but if you look at, if this was somehow x-axis, but F12 vector is negative of F21 vector. That means F12 plus F21, these two vectors must cancel. So we have this is a force, and this is another force, and so on this object you have two forces, and on this on this object you also have two forces. So let me write down it more simply. M1, there's a force F12, and there's a force, just put it in a direction, G1, and M2. M2 has to be in that line. M2 is over there, and there's a force vector F21, and maybe there's another G2. So this is the force. Just redraw. So we have this system M1 and this system M2. Now if you look at the two systems together, then we can say these guys are, this and this, they are examples of external forces. When you look at these guys and these guys, they are examples of internal forces on combined system. Okay, so let's write law for each one of them. So I'm going to write just for M1. So for M1, is going to be momentum of 1 dp1 dt is just going to be g1 vector external plus f12. So that's going to be law for m1. Law for m2 will be the p2 vector dt equal to external for these externals plus f21 vector. Now if I add these guys up, then I'm going to get on the right side, left side, I'm going to get d over dt. Now these guys can be combined as 1 p1 plus p2, right? And that's, then you have a external guys, you can combine them in a vector way, and we are going to have plus f12 plus, and these are internal guys, and we already learned internal forces should cancel each other from the third law. So this goes to 0, and this is all external. So let's call this f external. This is the net on 1 and 2, so we can just call it net. And this is just adding up the momentum of each one of the particles. So it's going to be p total vector. So p total vector is basically momentum of each one of them added up. Everything that you have in your system, you can add them up and you can get total. So like if I have two objects, 1 and 2, and they might collide, total will be just add for this guy, and then it's going to be total momentum. So now this law rate, let's write for p total equals to f net external. So now it's like this is a very complete law. I can have many particles, and in the end it will all end up like that. I just did with 2, but I can have many of them, and so you can have 1, 2, 3, 4, and this is, I'll have to do the total for that, and just everything is time following time. So this is the law. So now I can say that say there were 4 of them, suppose, at say ti, and these guys are moving in a random way, and at some other time, and any arbitrary time you look at it, start like this, and some arbitrary time, maybe this is 1, 2, 3, 4, maybe they've collided and now there are 5 of them broke up, whatever. Breaking up also internal, so even 5 of them. But if you look at the momentum of these guys, so this is for any arbitrary time p total, and so this is total at initial times. They were like this, and t is arbitrary. This will tell us what to do. Just integrate like we did earlier in the earlier video. So it tells us that if I integrate this from some initial to some arbitrary, so from this value, let's call I, and this, let's call it f. So we went from ti to t. So this is the impulse from ti to t of all the external forces is equal to p total at time t minus p total at initial time. So I can bring it over here. P total at some arbitrary time t equals p total at ti plus I use I, let's call it, keep using consistently, j external t to ti to t. And this external, right, this would be 0 if no external forces. Okay, so we conclude if no external forces, then see at any arbitrary time, don't have to pick a particular instant in time, just any arbitrary time, then P total T is independent of time. The only thing be true for initially I had this, and at any other time is the same value, that means this whole thing is independent of time. Okay, and that just means P total is always conserved in these no external force situations. Now this, if this is 0 for a particular t, it doesn't count, right? And 0 for every t, that means the only reason it can be 0 for every t is that there's no external force. So the system is isolated, and isolated systems cannot have change in momentum. So now let's see, how does this work out in collision? So in collision, what happens is when you have an object 1 and object 2, say it's going to collide. So let's look at just before the collision. So here is maybe 2 is sitting there, no problem. So just before the collision, it just touches. Just when it touches, it presses this internal force. So 1 will apply a force on that. So this is F2 1. So this on 2 by 1, and you should have exactly opposite force on 1, force on 1 by 2, on 1 by 2, and these are internal forces. So in this instant, whatever will happen to 2, maybe 2 will go that way, and maybe 1 will retreat or just stop, who knows, okay? Just situation dependent. So because this only internal forces, so this is a situation which we can call Pi total, and this situation we can call P final total. So this is, or sometimes called before and it's called after. So whatever suits your, so this should be equal, and that is the application of conservation momentum in a collision problem. Okay, now say 2, instead of going like that, what happened is 2 to remain what it is, some V, but this guy broke into two pieces and become 3 and 4. Maybe it's flying this way, fly that way. Okay, so this is M3, M4, M2. Now this still is internal. So this breakup process is still internal. So you'd look at this momentum, this is same. Regardless of what happened. That's the beauty of it. So this is a momentum conservation. As long as internal, force is internal, you're completely allowed to just forget there are forces between them. Okay, yeah, energy and all those things may be affected, all right, but the momentum will not be affected from just the internal forces. All right, so this is really this is the principle. I'm going to stop here because there's something to ponder about, right? Where the collision come from, and how the laws are kind of all tied together, right? The laws all tied together, and we can do problem of. So next, I'm going to do collision problems like this kind of thing. So this guy comes in, and these are threads collides. Maybe this guy comes in, still at rest, but after collision, one piece goes up, one piece goes down, and third piece, what will happen to the third piece? So this was 1 and 2 before the collision, but 3, 4, this 3, 4, and 5, 4 and 5 go this way, and what will happen here? So we're going to do these kinds of problems, but I don't want to make the video too long. I'm going to talk about this in the next video.